Yeah, we started talking about chapter 16 and acids and bases. And remember, an acid is really anything that can produce H plus ions in solution. And again, what we're talking about here is the ability to produce free floating H pluses, so not attached to anything, just to be able to kind of release into the solution these hydrogen ions along the way. Remember as well that the H plus ion, which is the hydrogen ion, and H3O plus, which is the hydronium ion, is essentially the same thing, and it sort of can replace each other in formulas and also equations as well. So anywhere there's an H plus really is that's the same as H3O plus, which is again is the hydronium ion. Also, as we also saw, H plus is also sometimes referred to as a proton in acid-base chemistry as well. Again, because it's pretty much just left with a proton when it's in the H plus form as it had only an electron and no neutrons. A base, on the other hand, is something that can produce, again, free OH minus ions. And same idea in the solution, be able to kind of release or create these freely floating OH minus concentrations. And as we'll talk about and sort of touched upon last time as well, really the ratio of sort of the amount of free H plus in the solution to OH minus will determine whether or not, again, a solution is going to be acidic, basic, or neutral, depending on which one is sort of larger. Um, there's sort of a more generic or general definition of an acid and a base, and that's the Bronsted-Lowry definition. And an acid is a proton donor, and a base is a proton acceptor. And as we talked about, remember that when they sort of donate or accept that H plus, thank you, is not just the hydrogen, but it is the plus. So it does affect sort of what is sort of made on the other side in terms of the charge. So if you did have something like, say, HCl and dissolving in water, basically. Here, this is going to be our acid. This is going to be our base. So the acid is going to send the H plus over. And the result of this, as we talked about, is we will actually form some partners on the other side of the arrow. And these are the partners. And the acid on one side of the arrow is related to the conjugate base on the other side. While the base on one side of the arrow there is related to the conjugate acid on the other side. So your regular sort of acid and bases on the left-hand side of the arrow, your conjugate partners on the right-hand side of the arrow. And as we talked about and as we saw, the absolute only difference you could have is this difference right here. The only difference is a 1H plus difference between those two things in order for them to be acid conjugate base pairs. So as we go from the base to the conjugate acid, because it does accept the 1H plus, it will end up with one more H plus, and this guy will end up with one less H plus as it goes from one side to the next. And we again could see our charges change. So here we lost the hydrogen on this side, and it was neutral. So it goes from being neutral to one more negative and is -1. Here, the water again is neutral, gains the hydrogen, becomes one more positive. So when you're writing sort of the conjugate acids are conjugate bases, you do need to make sure you do adjust the charge as well. Otherwise, again, be sort of incorrect. Any questions on that stuff there? All right, so I thought we were in the middle of this idea of what was Kw, and water can react with itself. It's amphoteric, and it can act as an acid or a base. And there is this relationship, which is an important relationship, which is again known as Kw, and that is the concentration of H plus times concentration of OH minus. is equal to 1 times 10 to the minus 14. As I mentioned before, once again, you can substitute that out for H3O plus, same thing. And remember that when we do see these little brackets, it does mean concentration. And basically it means molarity is the moles per liter is basically what it means. So we can use this sort of equation, as you can see on the bottom there. You can rearrange it and you can solve for either one, either the H plus concentration or the OH minus concentration. And they're both really the same calculation, which is kind of good. It's basically the Kw value, which for our purposes here, you could assume is a constant value, always the same number, 1 times 10 to the minus 14. So you got to think of that as one of those kind of numbers that you just have available to you. Once again, it's never really mentioned in a problem or anything like that. It's just sort of, they assume you know it. 1 times 10 to the minus 14 divided by the other concentration will give you either the H plus or the OH minus concentration. Once again, as we talked about at the end, you definitely want to make sure you are, again, using your exponent button when you're in this chapter. Otherwise, you're going to really find yourself off on your answers. So make sure you are punching in scientific notation correctly. So what can we do with that information? Well, once we calculate the H plus, which is essentially the acid part of the solution, and the OH minus is the base part of the solution. If we calculate the H plus concentration and it is larger than the OH minus concentration, then we should have an acidic solution. If we calculate that the OH minus, which is the base part of the solution, is larger than the H plus concentration, then we should have a basic solution. And if you calculate that the H plus concentration actually equals the OH minus concentration, at that point they both will equal 1 times 10 to the minus 7. Then you will have a neutral solution. So this is one way we could determine whether or not a solution is acidic, basic, or neutral by comparing the H plus to the OH minus concentration and seeing which one is larger. And that will give us our sort of answer there. All right, so why don't we try some here? These are 4 separate problems. So for each of them, calculate either the H plus or OH minus concentration, depending on which one's given. So whichever one's given, calculate the other. And then determine, is it acidic, basic, or neutral, each of these solutions. Look, so we'll start here with the first one here, which I think is that one. So we are given the H plus concentration. So once again, we can use that Kw. That is our H plus times our OH minus equals 1 times 10 to the minus 14. Once again, it is the same calculation sort of regardless of which one you're given. So we're going to do OH minus is 1 times 10 to the minus 14. And we're going to divide it by our H plus concentration, which is 3.4 times 10 to the minus 4. So remember, again, I want to punch this in correctly in your calculator. So like a 1, an exponent button, your negative button there, and 14. And then we're going to divide it by 3.4. Once again, your exponent button, your negative button, and 4 there. And if you do all that good stuff there, you are going to get a number. Looks like maybe 2.9 to the minus 11 here. This does need units as it is a concentration, so it is typically molarity there. Any questions on that calculation there? Now that we have the OH minus concentration, we want to compare it to our H plus concentration. So in this particular case, which one is bigger here? It is the H plus concentration is larger, and that would mean that this solution should be acidic. A reminder that when you are looking at numbers in scientific notation, the smaller negative exponent is the larger number. Because, minus 11 means you're going to go 11 places to the left and put a bunch of zeros, right? And to the minus 4, you're only going 4 places to the left and putting some zeros. So it's going to be actually the bigger number in that case. Yeah. Any questions on that there? All right, look at the next one. Pretty much same calculation here. We're going to go, we're using our Kw, our OH minus, going to equal our 1 times 10 to the minus 14. In this case, divided by our H plus concentration, 2.6 times 10 to the minus 8. And punching all that in the same way as the first one here is going to give me an error. No, I'll try that again. 10 to the minus 14 divided by 2.6 minus 8. It's going to get me a 3.8 times 10 to the minus 7 molar. Again, if your calculator is not in scientific notation, which it probably might not be, got a 60785 probably, or 385 as their calculator. Again, here we're going to compare these two, and in this particular case, it is actually the OH minus that is the larger value, and that would mean that this guy would be basic in this case. And your calculator may not give you a scientific notation. You'll have a bunch of zeros and stuff like that. But continuing on here, next one. Here we have the OH minus concentration given to us. We're looking for the H plus concentration. And once again, it doesn't really matter which one's given to you. It is really the same calculation. So this is the H plus. Again, going to use our KW number, 1 times 10 to the minus 14. In this case, divided by our hydroxide. And that's going to get us here. Looks like 1.6 to the minus 6. And again, molarity is the units. And here we are, oops, that's the H plus actually in this case. And we're going to compare these two. And once again, we do see in this case here, it looks like our H plus is larger than our OH minus. And that's going to tell us it is acidic in this particular case. Lastly, here on this one, once again, given an OH minus concentration. So solving for our H plus, 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. Popping that into your calculator using your exponent button. Looks like a 1.2 to the minus 12 in this case. And again, that is the H plus concentration. So comparing those two here, this is a much larger. So the OH minus here is larger than the H plus. And that would make the solution basic. Questions on any of those calculations? So again, most people struggle with punching it in the calculator. Yeah, so again, make sure that exponent button is used. All right, let's take another one here. What is the OH minus concentration if the H plus 2.8 times minus 5? And is it acidic or neutral? Okay, so OH minus, again, in this case, going to be using our KW value, 1 times 10 to the minus 14, divided by 2.8 times 10 to the minus 5. That is going to get us here. Looks like 3.6 to the minus 10 in this case. And in this case, if we again compare our OH minus to our H plus, we can see H plus is larger, so our H plus is greater than our OH minus. And again, this solution should be acidic. Any questions on KW, calculating H plus, OH minus? Again, H plus here, also the same thing. If you were asked to calculate the H3O plus, the same calculation, same deal. All right, we're going to skip this one, I think. Next thing we're going to talk about is actually the pH scale. And the pH scale runs from 0 to 7 to 14. And that's just for PowerPoint, no negative there. So our pH scale, 0 to 7 to 14. Less than 7 is acidic. Above 7 is basic. And really 7 on the nose there is neutral. 7 is sort of our center point, and as you go closer to 0, kind of in this direction, you're becoming more acidic. And if you head towards 14, you're becoming more basic in that case. So to calculate the pH, that is the formula on the bottom there. Let's just take a look at it here. So the pH here is equal to negative log of the H plus concentration. The actual name tells you what you need to calculate it. pH means you need the H plus concentration to calculate it. This again is another one of the formulas here that will be shown like this, and it is again the same thing. So whichever sort of way you want to look at it. So to calculate the pH here, it does depend on the type of calculator that you have as to how you punch it in, but since you're required to have a certain calculator, you have basically a non-display calculator, but I'll show you how to do it on both just in case you have a different calculator handy when you're doing some problems. So if you have a display calculator, and to know whether you have a display calculator or a non-display calculator, all you have to do is just hit log. And if it says error on your calculator, you have a non-display calculator. If it says log on your calculator, you have a display calculator. The one they make you buy for this class is a non-display calculator. It should say error when you hit log button on yours. But for a display calculator, if you do hit log and it actually says log, you would punch this in. You would start with the negative button. You would hit the log button, and then you would do your H plus concentration, making sure to use your exponent button as you punch it in. And then you would hit equals. Now for the calculators we have in here, they're really non-display calculators. And that means all these formulas in this sort of chapter here, you do have to kind of punch it in backwards, starting from the back of the formula and kind of punch it in that way into your calculator. So you actually have to start with the number. So you would start with the H plus concentration. You would then hit the log button, and then you would hit the negative button. And that would get you to the answer. And again, that is most likely, if you have obviously the correct calculator for this class, that is how you should punch it into this one. If you have more of a display calculator somewhere else, you're doing homework or something, then you would want to go the top way in terms of how to punch it into the calculator. So again, we calculate the pH. pH is just a number, and depending on where it falls on the scale, it will tell you if it's acidic, basic, or neutral. We are going to use 7 on the nose as neutral, and that's really because, as we just saw there with KW, if you calculate the concentration of H plus and it equals OH minus, they both have a concentration of 1 times 10 to the minus 7, which means that if you put that into the pH, you'll get a pH of exactly 7, and that's basically what neutral is. So it's got to be pretty much right on 7 for it to be neutral. If it's a little less than 7, it'll be slightly acidic. If it's a little more than 7, it'll be slightly basic. And we'll just kind of use 7 on the nose there. So let's talk about pH and sig figs and how far we should take our pH readings to. Are a calculation similar to pH? When you calculate the pH of a solution, the number of decimal places you should take your pH value to is equal to the number of significant figures there are in the concentration. So we are going in this case from significant figures to decimal places. So the concentration value that you're using to calculate the pH, for example, the H plus concentration, however many sig figs there are in that number is how many, not sig figs in your pH answer, is how many decimal places you should take the pH to. So for example here, if I had an H plus concentration, again, this is not negative, it's just from PowerPoint. If I had an H plus concentration of 1 times 10 to the minus 5, why don't you grab your calculator, make sure you can punch it in correctly, get the pH. Okay, so again, we're going to calculate the pH, which is negative log of the H plus concentration. And once again, it tells you what you need. We do have the H plus or the H3O plus here. And again, if you have a display calculator, which most of you do not because we are has to use a special calculator here, you would punch it in this direction. If you have a non-display like we do in this class, you're going to be again punching everything in this direction. So if you it's your non-display calculator, you would start with 1, you would hit your exponent button, you would hit your negative button, and you would hit 5, and that would be just putting this number in correctly into your calculator. You then would hit the log button, and then you would hit the negative button, and then staring at you on your screen should be a 5. Or again, in case you do come across a display calculator and you're doing something, you would punch it in exactly the way it's written, which means you would start with your negative button, you would hit your log button, you would type in your concentration 1 exponent button, negative button, and 5 equals also should be staring a 5 at you. Any questions on how to punch it in there? So at this point, 5 is our answer. We do want to make sure that we do give it to the proper number of digits in this case. And that means, is my answer, should it be 5? Should it be 5.0? Should it be 5.00? What should be the proper way to give this answer? So the rule is when we look at the concentration value, which is this has 2 significant figures. And when we go to our pH value, we are not going to do 2 significant figures, but that tells you how many decimal places you should take it to. So you should actually take it to 2 decimal places. So it is, in this case, significant figures to decimal places. By the way, we're going to talk about going in the other direction, going from pH back to concentration works the same way. If you have a pH value that has 2 decimal places, when you calculate your concentration, it should have 2 significant figures. So sometimes people get these, I always think sig figs is sig figs kind of deal on this. So it's again, sig figs to decimal places. First off, any questions on that there? By the way, this is acidic, basic, or neutral. This should be acidic, yes, less than 7. By the way, when you are asked that question, is it acidic, basic, or neutral? There is only one answer to that question. It should not be acidic and basic at the same time. I've never had anybody give me all 3, but I've had lots of people give me both, like it's acidic and basic. And we'll talk about why people do that in a little bit here. But if you're asked that question again, should be either acidic, basic, or neutral. Should not be more than one of those things. You should always look at the pH scale as well because that is the scale everybody pretty much has in their head. So that's really the value you want to kind of look at when you're looking at. Any questions on that there? All right. All right. So why don't we give it a go here? 2 separate problems. First one, second one. Calculate the pH for each of these and determine is each of them acidic, basic, or neutral. Okay, let's take a look. So on the first one here, we have the H plus concentration. Remember, that is what we need to calculate the pH. So again, pH is negative log of the H plus, which means we could go right in there, negative log of 2.1 times 10 to the minus 5. Again, with your non-display calculators, and go 2.1, exponent button, negative button 5. Going to hit the log button and the negative button one more time. And if you do all that good stuff there, going to get a 4.68 pH in this case. Again, 2 significant figures here, 2 decimal places here. First up. This again would be less than 7. So here we are looking acidic here in this situation now. All right, so let's take a look at number 2 here. And we want the pH. So again, pH is equal to negative log of the H plus concentration. Problem here is that is not the H plus concentration. That is the OH minus concentration, which means we might need to use perhaps KW here, like we did earlier, or 1 times 10 to the minus 14 divided by our OH minus 5.9 times 10 to the minus 8 in this case. That is going to get us here 1 to the minus 14 divided by 5.9 to the minus 8. And we'll go 1.7 to the minus 7. And now that we have the H plus concentration, now we could go in there. So that will be negative log of 1.7 times 10 to the minus 7. And that's going to get us here 6.77 as our pH, slightly below 7. This is slightly acidic here in this particular case. So you want to make sure that you are doing the correct thing. If you did this calculation where you took the pH is equal to minus the log of 5.9 times 10 to the minus 8, you ended up with a number of 7.23. What you calculated here is not the pH because once again, that is the OH, but you did calculate something. You calculated what is known as the POH. So you did calculate something, lies down the road, that is kind of useful. The POH is a scale similar to the scale, but it's different. I would not consider it bad thing. We'll see here in a second. There's a lovely relationship that if you take the pH plus the POH equals 14, which means you take 7.23, take 14 minus 7.23, you get yourself to the pH pretty easily. A few ways to get there, but you want to make sure that you are calculating what you want to calculate. Problem. First off, any questions on that? Okay. All right. The pH scale is based on the log of 10. So as the concentration of H plus changes by a power of 10, so is the pH. So if you have an H plus of 1 times 10 to the minus 3, the pH is 3. If you have a pH of 1 times 10 to the minus 4, the pH is 4. 1 times 10 to the minus 5, pH is 5. As the H plus concentration increases, the pH decreases. And the lower the pH, the more acidic it is. Remember as well that relationship that we saw earlier, as the H plus concentration goes up, the OH minus concentration goes down and vice versa. So the higher the H plus, the lower the pH will be, the higher the OH minus, the lower the H plus will be, and the higher the pH will be. And that's because, again, in the case, you got more OH minus than you do H plus, you're going to get yourself into a basic pH and a higher pH. If you have more H plus in the solution than you do OH minus, you'll have a lower pH and probably into the acidic solution. Now, there are a few different ways that you can measure pH. You can use a pH meter, which is a nice way because, frankly, it just digitally gives you the pH when you put the electrode in the solution. How does it actually work? Where the electrode there basically measures the H pluses that are floating around in that solution, the amount of H plus in that solution. It does so basically by measuring voltage. So you give it like a pH of 4, a pH of 7, a pH of 10, and you calibrate your pH meter. It makes like a little standard curve line. And then when you put it in your solution, it goes, oh, that voltage is like a pH of 3, or that voltage is a pH of 9, or something like that, using the calibration. You could also use, like we'll do today, I think in lab, some pH paper. pH paper, you put it in the solution, it changes colors. A lot of times there's multiple little squares on it. You try to go to the little key here and match up which one sort of matches the best and kind of do your pH based off of that. Obviously, not as accurate usually as the pH meter because it's just usually just like it's a pH of 1, 2, 3, 4, kind of whole numbers and stuff like that. Almost like if you ever tested a swimming pool, they have those little pH type papers or tester strips that you put into your pool and it kind of changes color and stuff like that. A couple other ways that we determine, for example, if a solution is acidic or basic, will not tell us the pH, but we can use litmus paper. And litmus paper is typically either red or blue. They also have neutral litmus paper as well. But basically, if your litmus paper, you put your solution on, it stays red or turns red, that usually means the solution is acidic. Again, it will not tell you the pH. Or if your litmus paper stays blue or turns blue, it usually means it is basic. Yeah. So if your litmus paper turns red, acidic, turns blue, it's basic. Or obviously stays on those colors, it's acidic or basic, depending on what you got. This is the pH scale. And again, you can see up here sodium hydroxide, which is a strong base up there around 14. 1 molar HCl down there by a pH of 0, pretty close to it. And we got some acids, a lot of cleaners are bases. Pure water, pH is 7. If you actually take water that's maybe not pure water or water that sits out for a while, pH will definitely probably not be 7. pH will probably be in this range, in that park here, be slightly acidic. And that's because it picks up CO2 in the air and creates carbonic acid, which increases the H plus concentration in the solution and lowers the pH and stuff like that. So sometimes people are surprised they test water in the lab sometimes and it's like, whoa, it's kind of acidic. And again, that's very common. But now for a while. Now, we just touched upon this in the last problem. There definitely is similar scales to pH, and one of them is the POH scale. And as I said, a really nice relationship between pH and POH is basically the equal 14. So it does give you a variety of ways that you could calculate some of these problems. I'll put in our pH in there. I'll also put in our KW that we saw earlier. So as you can see, you might not need to use KW to get the H plus concentration like we did in that last problem. You could just calculate the POH and then it's basically subtract 14 and get yourself to the pH. So it's a nice little workaround. Or you could still use, like we did in the problem, KW there to get the H plus concentration, then go into the variety of sort of options as to how to. Um, Now, the pH scale, as we talked about, goes from 0 to 7 to 14. Once again, acidic of below 7, basic, and then neutral. The POH scale runs opposite. It also is 0, 7, and 14. But below 7 will be basic on the POH scale. Above 7 is acidic, and this is neutral. So what happens is people will sometimes calculate the pH and go, cool, it's below 7, it's acidic, and then they'll calculate for the exact same solution problem the POH and go, cool, it's above 7, it's basic. And that's how people give that answer of it's both acidic and basic when they're asked that question, because they calculate one and go, cool, it's above 7, one is below 7. So remember, when you are looking at whether or not something is acidic, basic, or neutral, I would always look at the pH scale, because I'll be honest with you, most people don't have this scale in their head. Most people have the pH scale in their head. And if you just look at the pH, you will hopefully get the right answer. They are opposites of each other, as you can see there before I cross it out. If you have a high pH, you will have a low POH and vice versa on it. Any questions on that there? Now, while we got a little bit of room there's two more types of calculations you could do that all give you a variety of ways, or maybe an alternative way to solve some of these problems. And that is if you are actually given the pH, so if you actually have the pH given to you, directly from it, you could actually get the H plus concentration. So if you have the pH given to you, you can directly calculate the H plus concentration. To calculate the H plus concentration, if you are given the pH, it is equal to the inverse log of the negative pH. On most people's calculators, probably not yours because it's a non-display calculator, when you hit inverse log, that is put a 10 and a caret up there. You want to make sure it's negative pH when you do that. How do you do the inverse log on the calculator? The inverse log is usually top left corner. There's a second button or a shift button top left corner of your calculator, and then the log button. Yeah, and that will basically get you it. On top of the log, it will say like 10 to the x or something like that. Usually also known as how some people still maybe do scientific notation, which clearly if you're doing that, you're going to be really screwed in this chapter because now you're doing really bad calculation for sure. You definitely do not want to make sure you use those exponent buttons. By the way, if you were given the POH, you could get the OH minus concentration directly from it as well. It is the exact same calculation. The OH minus is equal to the inverse log of the negative POH. And again, on a display calculator, it will pop up a 10 and a caret when you hit those buttons. Again, on yours, it really will not. But once again, on yours calculator, you do need to work backwards on this calculator in the non-display. So for example, if we had our pH of 5 that we had earlier, and we wanted the H plus concentration, once again, we would be doing that the H plus concentration is the inverse log of the negative pH. So the way that you guys would punch it into your calculator in a non-display calculator is you would actually start with the pH. You would hit 5. Then you would hit the negative button to make it negative. Then you would hit the second button. And then you would hit the log button. So that would be the way that you would do it on your calculator. 5, negative button, second, and log. And it will get you your H plus again. On your calculator, it will probably display it in non-scientific notation, or that is 1 times 10 to the minus 5 molar in this case. Questions on that? Obviously, once again, if you did have a display calculator, you would be going in this direction with the formula. You would be hitting the second button. You'd be hitting the log button. You would be hitting the negative button, and then you would put 5 in if you had a display calculator, and then equals. And since you have a non-display, that is how you would put that guy back. By the way, as we went backwards, as you can see here in this example, the rules apply in the reverse direction. We had 2 decimal places. Our answer ended with 2 significant figures. So again, works the same way going in the backwards directions. Any questions on that? So here, as you can see, there is a variety of answer as long as you get. And it's really kind of dependent on the information given to you as to which way you want to go. And in a lot of cases, you can't have that multiple sort of ways to get to the answer. All right, so 2 problems here. So why don't we practice everything here? So for the first one, what is the pH? What's the POH? And what is the OH minus concentration? And is it acidic, basic, or neutral? For the second one, what is the pH, the POH, the H plus concentration? Okay, let's take a look, see how you're doing. So we'll start with the first one here. We are given the H plus concentration of looks like 3.6 to the minus 9. And since in this particular problem, we're really looking to solve for everything. Right off the bat here, we have two options of what we could get to. We definitely can, if we wanted to use KW like we did earlier, and we could go to the OH minus concentration, or we could go right into the pH. And I'm going to choose to go right into the pH at this point. So that's the first thing I'm going to calculate here, which is the pH is equal to negative log of our 3.6 times 10 to the minus 9. Once again, we want to punch that in correctly, so we're going to go 3.6 exponent negative 9, hit the log button, hit the negative button, and that's going to give you a pH of 8.44. Once again here, now that I have the pH, that opens up possibilities of me going to get the POH as an option. I could also get the uh, back and still get the OH minus using KW. So it's up to you. For me, I'm just going to roll and get my POH from that. So that just seems easy. Once again, the pH plus the POH is equal to 14. That means our POH in this case would be 14 minus our pH, 8.44. That's going to get me a POH of 5.56. At this point, you now have two options still in oxide. You use KW like we did earlier on in this chapter, or you can use that inverse log there now that you have the POH. And that's what I'm going to do here. So I'm going to use the POH value I just got and use that to get to the OH minus. And again, that's going to be the inverse log of the negative POH. And once again, on your kind of non-display calculators you guys have, we're going to start with the number. So you're going to go 5.56. You're going to hit your negative button to turn it negative. You're then going to hit your second button and your log button. And again, in this particular case, I think I got that going there. That is going to get you, we'll go here. Again, you may not have it in scientific notation. 1, 2, 3, 4, 5, 2, 7, 5, it looks like. So that's going to get us a 2.8 times 10. 1, 2, 3, 4, 5, 6 to the minus 6 molar. And remember, it does need a unit since it is a concentration. Once again, that should be pretty much the same number you get if you use KW, which would be 1 times 10 to the minus 14 divided by 3.6 to the minus 9, which is the H plus concentration. And you should get the same number if you chose the KW way as well. Same idea. We had 2 sig figs here. 2 decimal places, 2 decimal places, 2 sig figs. And the last thing we're looking at in this case is it acidic, basic, or neutral? So once again, looking at the pH value, that is 8.44, which means this guy is going to be basic in this case. Any questions on any of those there? All right, so looking at number 2 here, in this particular case, we are given the OH minus concentration. So that also opens up really 2 options since we're looking for everything. We could use KW to get the H plus. We could also get the POH directly from that value. So I'm going to start with the POH in this case. And the POH is going to be negative log of the OH minus. That's negative log of 9.2 times 10 to the minus 2. Once again, punching that into our calculator in the non-display way, you're going to go with the number 9.2 exponent negative and 2. You're then going to hit the log button and then the negative button. And if you do that, That's going to get you a pOH of 1.04 in this case. At this point, it does again open up a couple of options. For me, again, getting the pH at this point is pretty simple. We're just subtract from that number. So the pH here going to be 14 minus 1.04. And that's going to get us here. Looks like 12.96 in this case. And in this particular case, we now have, again, a couple of options as to how to get our H plus, but I'm going to do the inverse log here. So for our H plus, it's going to be the inverse log of negative 12.96. And again, on your non-display calculator, 12.96 goes in first, negative button to make it negative, second, and log. Must be better to hit the actual right button would probably be good, I imagine. Try that one more time here. So, there we go. That's going to get us a 1.1, it looks like, times 10 to the minus 13 molar. And once again, should be the same thing you get if you did kW. 1 times 10 to the minus 14 divided by our 9.2 times 10 to the minus 2 should also get you there as well. All right, so once again here, looking at the pH value here, which is 12.96, that again is going to be basic. Any questions on any of those calculations? So as you can see, there are a variety of options depending on sort of which path you take. They all should, again, get you in the right spot. All right, I want to try this one. pH of 5.67. The pOH is... All right. So obviously here we have pH given to us. So the easiest thing obviously to do is the pH plus the pOH equals 14. That's going to give us a pOH that's equal to 14 minus our pH, which would then be 14 minus 5.67. And that's going to look like a 8.33 on our pOH. Again, this solution is acidic because the pH is 5.67, less than 7 here. That's all on that one. All right, we'll let it there for now.